The discovery of electric charge, from ancient curiosity to atomic insight, ladies and gentlemen, to understand why atoms have charges, we must travel back to a time when the word atom did not yet exist in science, when electricity was not harnessed to power cities, and when the mysterious force we now call charge appeared only as a strange attraction between everyday objects. The story of electric charge does not begin in a high-tech laboratory. It begins with curiosity, with simple observations and profound questions. More than 2,000 years ago, in ancient Greece, thinkers were already fascinated by the hidden forces of nature. Among them was Thales of Miletus, who observed something remarkable. When amber, a fossilized tree resin, was rubbed with fur, it could attract small bits of straw or feathers. This phenomenon seemed magical. There was no visible connection between the amber and the objects it pulled toward itself. No strings, no magnets, just an invisible influence. The Greek word for amber was electron. That simple word would echo through history, eventually giving us the term electricity. But for centuries, this curious property remained little more than a philosophical puzzle. It was seen as a novelty, not yet understood as a fundamental feature of matter. In those early days, nature was explained through philosophy rather than experiment. Greek thinkers like Democritus proposed that all matter was made of tiny indivisible particles called atoms. Yet even this bold atomic idea did not connect directly to electricity. The attraction of amber was treated as a surface curiosity, not a clue to the structure of matter itself. As centuries passed, interest in electrical phenomena reawakened during the Renaissance. Scientific thinking began shifting from philosophical speculation to systematic experimentation. By the 17th century, natural philosophers were building primitive electrical machines that generated static electricity through friction. One key figure in this transformation was William Gilbert, who studied magnetism and static electricity in the late 1500s. Gilbert distinguished between magnetic effects and what he called electric effects, recognizing that they were different phenomena. Still, electricity was mysterious. It could attract objects, create sparks, and sometimes even produce small shocks. But what was it? Was it a fluid, a substance, a force? Many scientists believed electricity involved some invisible fluid flowing between objects. The 18th century brought dramatic progress. Experimenters began systematically studying electrical behavior. One of the most famous among them was Benjamin Franklin. Franklin proposed that electricity involved a single fluid that could exist in excess or deficiency. He introduced the terms positive and negative charge labels we still use today. Importantly, he also proposed the principle of charge conservation, that electrical charge is not created or destroyed but transferred between objects. Franklin's famous kite experiment during a thunderstorm demonstrated that lightning was electrical in nature. This realization was revolutionary. The sparks seen in laboratories and the lightning bolts in the sky were manifestations of the same phenomenon. Electricity was not a minor curiosity, it was a universal force. Yet at this stage, electricity was still understood in macroscopic terms. Scientists could observe charge building up on objects, discharging as sparks, and flowing through conductors. But they had no idea that this behavior was rooted in tiny particles inside atoms. The next major breakthrough came with advances in the study of electromagnetism during the 19th century. Scientists such as Charles Augustin de Coulomb measured the force between charged objects and established what we now call Coulomb's law. This law showed that electric force follows a precise mathematical pattern. It increases with charge and decreases with distance squared. For the first time, electric charge was quantified. Then came a unifying vision from James Clerk Maxwell. In the mid-1800s, Maxwell developed equations that unified electricity and magnetism into a single theory of electromagnetism. His equations predicted electromagnetic waves, including light itself. Suddenly, electricity was not just about sparks and shocks. It was tied to the very nature of light and radiation. Even so, the nature of charge remained puzzling. Was it continuous, like a smooth fluid, or did it come in discrete units? The answer emerged at the end of the 19th century in a laboratory experiment that changed physics forever. In 1897, J. Thomson was studying cathode rays, mysterious beams produced in vacuum tubes. By applying electric and magnetic fields to these rays, Thomson discovered that they were composed of tiny, negatively charged particles. These particles were far smaller than atoms. He had discovered the electron. This was a turning point in human understanding. Atoms, once thought indivisible, were revealed to contain smaller components, and these components carried electric charge. Electricity was not just something that objects acquired through rubbing. It was embedded within the very structure of matter. Thomson measured the charge-to-mass ratio of the electron and found it to be enormous compared to known ions. This meant the electron was incredibly light. It was a fundamental constituent of all atoms. Suddenly, the phenomenon observed by Thales with amber thousands of years earlier had a microscopic explanation. Rubbing materials transferred electrons from one surface to another, creating an imbalance of charge, but the story did not end there. If electrons carried negative charge, where did positive charge reside? Atoms are normally neutral, meaning their positive and negative charges balance. This mystery led to further experimentation. In 1911, Ernest Rutherford conducted his famous gold foil experiment. By firing alpha particles at thin gold foil, he observed that some particles were deflected at large angles. This result suggested that atoms contain a small, dense, positively charged nucleus. Within this nucleus were protons, particles carrying positive charge equal in magnitude to the electron's negative charge. The atom was no longer a featureless sphere. It was a structured system with negatively charged electrons surrounding a positively charged core. At this moment, electricity and atomic structure became inseparable. Charge was no longer a surface property or mysterious fluid. It was a fundamental property of subatomic particles. But another crucial question remained. Was charge continuous or discrete? Could you have half an electron's charge? The answer came from experiments by Robert Millikan in 1909. Millikan's oil drop experiment measured the charge of individual oil droplets suspended between electric plates. By carefully balancing gravitational and electric forces, he determined that charge always appeared in integer multiples of a smallest unit, the charge of the electron. Charge was quantized. This discovery paralleled the emerging ideas of quantum theory. Just as energy comes in discrete packets, so too does electric charge. There is a smallest unit, a fundamental chunk of electricity. Now the pieces were coming together. Ancient curiosity had evolved into precise measurement. Amber's attraction to straw was explained by the transfer of electrons. Lightning was the discharge of massive electrical imbalances in the atmosphere. The electric force between objects followed strict mathematical laws. Atoms contained positively and negatively charged particles whose charges balanced perfectly. Yet even with these discoveries, the deeper nature of charge remained elusive. Why do electrons have exactly that amount of charge? Why are proton and electron charges equal and opposite? Why does charge come in discrete units at all? By the early 20th century, physics was undergoing another revolution. Quantum mechanics was reshaping our understanding of matter and energy. Charge was no longer viewed merely as a property of particles, but as something connected to deeper symmetries in nature. Still, the historical journey to this point is remarkable. Over thousands of years, humanity progressed from observing static sparks to probing the internal structure of atoms. Each stage required both curiosity and courage, the willingness to question accepted beliefs and follow experimental evidence. The discovery of electric charge illustrates a powerful pattern in science. It begins with observation, a piece of amber attracting straw. It advances through measurement, Coulomb's careful experiments. It deepens through theory, Maxwell's equations. And it transforms through discovery, Thomson's electron, Rutherford's nucleus, Millikan's quantized charge. What began as a mysterious attraction became a cornerstone of modern physics. Today, we understand that every atom contains charged particles. The behavior of matter, from chemical reactions to biological processes, depends on these charges. The devices we use, the lights that illuminate our homes, the computers that process information, all rely on controlling electric charge. But none of this would have been possible without the long journey from ancient curiosity to atomic insight. Electric charge, once seen as magic, is now measured with extraordinary precision. Yet the sense of wonder remains. For when we trace the history of its discovery, we see not just a scientific achievement, but a testament to human inquiry itself. From Thales observing amber, to Franklin flying his kite, to Thomson discovering the electron, the story of electric charge is a story of humanity seeking to understand the invisible forces shaping our world, and in that journey we uncovered something extraordinary. The spark in amber was not just a curiosity. It was a clue to the structure of matter itself. To understand why atoms have charges, we must step directly into the interior of the atom itself. For centuries, atoms were imagined as indivisible building blocks of matter, tiny solid spheres that could not be broken down further. But the 20th century shattered that image. What scientists discovered instead was a dynamic structure composed of smaller particles, each carrying distinct properties, and among the most important of those properties is electric charge. At the heart of every atom lies a dense central region known as the nucleus. This nucleus is extraordinarily small compared to the size of the atom as a whole. If an atom were expanded to the size of a football stadium, the nucleus would be no larger than a marble placed at the center. Yet almost all the atom's mass resides inside this tiny core. Inside the nucleus are two types of particles, protons and neutrons. The proton carries a positive electric charge. The neutron, as its name suggests, carries no electric charge at all. Surrounding the nucleus, occupying the vast majority of the atom's volume, are electrons, tiny particles with negative electric charge. This simple arrangement, positively charged protons in the nucleus and negatively charged electrons around it, explains why atoms have charges. But it also raises deeper questions. Why do these particles exist? Why do they carry opposite charges? Why is the electron's charge exactly equal in magnitude to the proton's charge? The story of how this structure was uncovered is one of the most dramatic chapters in science. In 1897, J. Thomson discovered the electron through experiments with cathode rays. He showed that these rays were composed of tiny, negatively charged particles far smaller than atoms. This discovery revealed that atoms were not indivisible after all. Thomson initially proposed a model in which electrons were embedded in a diffuse cloud of positive charge, sometimes described as a plum pudding model. But this idea was soon challenged. In 1911, Ernest Rutherford performed the famous gold foil experiment. By firing alpha particles at thin sheets of gold, he observed that a small fraction of them were deflected at sharp angles. This could only be explained if the positive charge of the atom was concentrated in a tiny central nucleus. Thus emerged the nuclear model of the atom, a compact, positively charged core surrounded by negatively charged electrons. The proton, identified as the carrier of positive charge within the nucleus, has a charge exactly equal in magnitude but opposite in sign to the electron's charge. This equality is not approximate. It is exact to an extraordinary degree of precision. The positive charge of a single proton perfectly balances the negative charge of a single electron. When an atom contains equal numbers of protons and electrons, it is electrically neutral. This balance is fundamental. If the charges were not equal, atoms would carry residual charges that would dramatically alter the behavior of matter. The stability of atoms, and therefore the stability of chemistry and life, depends on this precise equality. The neutron, discovered later by James Chadwick in 1932, plays a different role. Although it carries no electric charge, it contributes to the mass of the nucleus and helps stabilize it through the strong nuclear force. Without neutrons, many atomic nuclei would fly apart due to the repulsion between positively charged protons. This brings us to a crucial insight. Electric charge is not simply a surface property of matter. It is built into the identity of subatomic particles themselves. The electron does not have negative charge as an added feature. Its negative charge is part of what defines it as an electron. Likewise, the proton's positive charge is inseparable from its existence. But what exactly is charge? In classical physics, charge is a property that determines how particles interact through the electromagnetic force. Opposite charges attract, like charges repel. This attraction and repulsion are described mathematically by Coulomb's law, which quantifies the electric force between charged objects. Yet the atomic picture reveals something deeper. The electron is not simply orbiting the nucleus like a planet around the sun. Early models suggested such planetary motion, notably in the work of Niels Bohr. Bohr proposed that electrons move in specific quantized orbits, each corresponding to a fixed energy level. These quantized orbits explained why atoms emit light at specific wavelengths. However, classical orbits turned out to be incomplete descriptions. With the development of quantum mechanics, scientists such as Erwin Schrödinger introduced a new framework. Electrons are better described as wave-like entities occupying probability clouds around the nucleus. These clouds, known as orbitals, represent regions where electrons are likely to be found. Despite this shift from planetary orbits to quantum wave functions, the role of charge remains central. The attraction between negatively charged electrons and positively charged protons binds the atom together. Without this electromagnetic attraction, electrons would drift away and atoms would not exist. It is worth pausing to appreciate the strength of this force. The electromagnetic force between a proton and an electron is enormously stronger than the gravitational force between them. Gravity shapes planets and stars, but within the atom, gravity is negligible. Charge, not mass, governs atomic structure. Yet there is a delicate balance at play. Electrons are attracted to the nucleus, but they do not collapse into it. Quantum mechanics provides the explanation. The electron's wave, like nature and the uncertainty principle, prevent it from being localized precisely at the nucleus. Instead, it occupies stable energy states. Charge creates the attraction, while quantum principles create stability. Another remarkable feature of atomic charge is its quantization. The electron carries a fundamental unit of negative charge, approximately -1.602 times 10 coulombs. The proton carries the same magnitude of positive charge. All observable electric charges are multiples of this fundamental unit. This means you cannot isolate a fraction of an electron's charge in ordinary matter. This quantization was confirmed through experiments like the oil drop experiment conducted by Robert Millikan. By measuring tiny droplets of oil suspended in an electric field, Millikan demonstrated that charge appears only in discrete units. Inside the proton and neutron lies yet another layer of structure. These particles are composed of even smaller constituents called quarks. Protons contain 2 up quarks and 1 down quark, while neutrons contain 1 up quark and 2 down quarks. Quarks themselves carry fractional electric charges, either +2/3 or -1/3 of the electron's charge. When combined in groups of 3, they produce the integer charges of protons and neutrons. This discovery deepened the mystery. Charge is not only fundamental at the level of electrons and protons, it extends into the substructure of matter itself. The pattern of charges among quarks is not random. It follows strict mathematical rules embedded in the framework of particle physics. Why do electrons and protons have opposite charges? One possible answer lies in symmetry. The laws of physics exhibit remarkable symmetry between positive and negative charge. For every particle with a given charge, there exists an antiparticle with the opposite charge. The electron's antiparticle, the positron, carries positive charge equal in magnitude to the electron's negative charge. This symmetry suggests that charge is woven into the fabric of the universe at a fundamental level. It is not an accident or an emergent property of atoms. It is part of the underlying structure of reality. The interplay between protons and electrons gives rise to the periodic table, chemistry, and molecular bonding. The number of protons in an atom's nucleus determines the element. Hydrogen has 1 proton, helium has 2, carbon has 6, oxygen has 8. The arrangement of electrons around the nucleus determines how atoms interact with one another. Chemical bonds form because of the sharing or transfer of electrons between atoms. Ionic bonds arise when one atom transfers electrons to another, creating positively and negatively charged ions that attract each other. Covalent bonds form when atoms share electrons. In every case, charge is the driving force behind chemical structure. Even the solidity of matter arises from electric charge. When you press your hand against a table, the sensation of contact is caused by the repulsion between electrons in your skin and electrons in the table's surface atoms. The electromagnetic force prevents atoms from passing through one another. Thus, the structure of the atom, with its charged components, explains not only abstract physics, but everyday experience. The shape of molecules, the colors of substances, the conductivity of metals, and the reactions that power living cells all depend on the arrangement of charged particles within atoms. And yet, despite our detailed understanding of atomic structure, the ultimate origin of charge remains mysterious. We can describe how protons and electrons carry charge. We can measure it with extraordinary precision. We can explain how it governs atomic interactions. But why does the electron have exactly that charge and not another value? Why does the proton match it so perfectly? Modern theories suggest that charge arises from deeper symmetries in quantum field theory. The electron is an excitation of an underlying electron field, and its charge reflects how it interacts with the electromagnetic field. In this view, charge is a manifestation of a fundamental symmetry of nature. But even this explanation pushes the question one step deeper rather than eliminating it. Why does the universe possess that symmetry? What is clear is this: the structure of the atom, with its positively charged protons and negatively charged electrons, is not arbitrary. It is the foundation of matter itself. The charges of these particles determine the architecture of atoms, the complexity of chemistry, and the possibility of life. When we ask why atoms have charges, we are really asking why the basic building blocks of matter carry this extraordinary property. The answer lies in the identity of the particles themselves. The proton's positive charge and the electron's negative charge are not optional features. They are essential characteristics. From the nucleus at the atom's center to the cloud of electrons surrounding it, charge defines structure, interaction, and stability. It is the invisible thread connecting the smallest particles to the largest systems, and within the delicate balance of positive and negative charge, the entire material universe finds its form. To grasp why atoms carry electric charge, we need to move beyond merely identifying particles and understanding their arrangement. Charge is not simply an attribute of electrons or protons. It is a fundamental property woven into the very fabric of reality. It governs how particles interact, how atoms combine, and how the universe behaves on both microscopic and cosmic scales. In this sense, charge is far more than a measurement or a label. It is a defining feature of the physical world. From the earliest observations of static electricity to the precise measurements of modern physics, scientists have come to recognize that charge is intrinsic to certain particles. It is not a property that atoms acquire under certain conditions, nor is it something that can be turned on or off. An electron is an electron because it carries a negative charge, just as a proton is a proton because it carries a positive charge. The value of these charges is fixed, consistent, and universal. The electron's charge is always -1, 602 times 10 coulombs, and the proton's charge is equal in magnitude but opposite in sign. This equality is not coincidental. It is critical to the stability of matter. The universality of charge has profound implications. If charges were variable or inconsistent, atoms would be unstable, chemical reactions unpredictable, and life itself impossible. The forces that hold molecules together, the bonds that shape proteins, the reactions that sustain metabolism, all depend on precise values of electric charge. Even the formation of planets and stars, though governed largely by gravity, is subtly influenced by electromagnetic interactions during the initial aggregation of matter in the protoplanetary disk. Charge is everywhere. It is the invisible scaffolding upon which the physical universe is constructed. One of the key reasons charge is fundamental is that it dictates the electromagnetic interactions between particles. Opposite charges attract, like charges repel, and these forces are described mathematically with astonishing precision. Coulomb's law quantifies the electric force between two-point charges, revealing that the strength of the interaction is proportional to the product of the charges and inversely proportional to the square of the distance between them. This simple yet powerful law underlies everything from the cohesion of atoms to the behavior of electric circuits. But charge is not only about attraction and repulsion. It is intimately tied to energy and dynamics. A charged particle moving in an electric or magnetic field experiences a force that can change its trajectory, accelerate it, or cause it to emit radiation. These interactions form the basis of classical electromagnetism, which James Clerk Maxwell unified into a set of equations in the 19th century. Maxwell's equations revealed that electric and magnetic fields are two sides of the same coin, that changing electric fields produce magnetic fields, and vice versa. This unification was revolutionary, showing that the behavior of charged particles is central not only to static interactions, but to the very nature of light and electromagnetic waves. While classical physics can describe the forces and movements of charges, it cannot fully explain why certain particles carry charge at all. For this, we must turn to the framework of quantum mechanics and modern particle physics. In quantum theory, the electron is not a mere point particle, but an excitation of an underlying quantum field. Its negative charge arises naturally from its interaction with the electromagnetic field, reflecting deeper symmetries known as gauge symmetries. These symmetries are abstract mathematical structures, but they have concrete consequences. They dictate which interactions are possible, enforce charge conservation, and determine the allowed states of particles. Charge conservation is one of the most fundamental principles in physics. In any isolated system, the total electric charge remains constant. It cannot be created or destroyed. When an electron moves from one atom to another, the overall charge in the system is unchanged. It is simply redistributed. This principle is not just a rule of thumb. It is a law of nature, deeply embedded in the symmetries of space and time. The conservation of charge ensures that matter remains predictable and stable, allowing atoms and molecules to form consistent structures over time. Interestingly, charge is not only associated with particles that we observe every day, like electrons and protons, but also with particles far more exotic. Quarks, the constituents of protons and neutrons, carry fractional charges. Up quarks have a charge of +2/3, and down quarks have a charge of -1/3. These fractions combine in groups of 3 to form protons +1 and neutrons 0. This fractional charge arrangement is not arbitrary. It is dictated by the mathematical rules of quantum chromodynamics, the theory describing strong interactions. The existence of fractional charges further emphasizes that charge is a fundamental, intrinsic property of matter, not something that emerges from larger structures. Beyond the particle level, charge has macroscopic consequences. The electromagnetic force, mediated by charged particles, shapes the behavior of atoms, molecules, and materials. It governs conductivity, magnetism, and chemical reactivity. It determines why metals can carry currents, why insulators resist them, and why semiconductors can be engineered to control the flow of electrons. The entire field of electronics, from simple circuits to advanced computers, relies on our ability to manipulate electric charge. Without charge, our technological civilization would be impossible. Yet, the presence of charge is also essential for life itself. Biochemical processes depend on the movement of ions, charged atoms or molecules, across membranes. Neurons communicate through rapid changes in voltage caused by the flow of sodium and potassium ions, creating the electrical signals that allow brains to process information. The contraction of muscles, the beating of the heart, and even the regulation of cell volume depend on electric charges and their interactions. In a very real sense, the property of charge underpins the dynamics of living systems. At a deeper level, the very structure of matter is stabilized by charge. Electrons are attracted to the positively charged nucleus, but quantum mechanics prevents them from collapsing into it. The balance of electromagnetic attraction and quantum behavior gives rise to discrete energy levels, which in turn determine the chemical properties of elements. This interplay ensures that matter forms the structured, stable, and complex forms we observe. Without charge, atoms would not exist in stable configurations, molecules could not form, and chemistry, as we know it, would be impossible. The universality of charge is also reflected in the symmetry of the universe. For every particle with a given charge, there is typically an antiparticle with the opposite charge. The electron has the positron, the proton has the antiproton. This symmetry is fundamental in theories of particle physics and underlies the stability of the laws governing our universe. When matter and antimatter meet, they annihilate, releasing energy. This balance of positive and negative charge is not only a microscopic detail, it is central to the overall structure of reality. Even the appearance of neutrality in the universe, the fact that most matter appears electrically balanced, is a consequence of this fundamental property. Atoms typically have equal numbers of protons and electrons. This neutral configuration allows complex structures to form without overwhelming electric forces tearing them apart. It is a delicate balance. A single excess of charge in one direction would radically alter chemistry and prevent the formation of stars, planets, and life. Charge is also intimately connected to the concept of energy. A charged particle in an electric field possesses potential energy. Moving, it converts that potential energy into kinetic energy. When charges accelerate, they emit electromagnetic radiation, light. This relationship between charge, force, and energy is central to understanding not just static electricity, but the behavior of light, radio waves, and even cosmic phenomena such as the radiation emitted by pulsars and black holes. The quantization of charge, first confirmed by Millikan's oil drop experiment, adds another layer to its fundamental nature. Just as energy is quantized in discrete packets called quanta, charge exists in fixed, indivisible units. The electron's charge is the smallest free charge observed in nature, and all macroscopic electrical phenomena are multiples of this unit. This discrete property links charge to the quantum world and emphasizes that it is not a continuous, arbitrary attribute, but a fixed, intrinsic feature of particles. Finally, charge is deeply tied to the unification of forces in modern physics. In quantum field theory, charge emerges from symmetries in the underlying fields. The electromagnetic force arises because particles carry a property, electric charge, that interacts according to specific rules. Theories that attempt to unify all forces, including the strong, weak, and gravitational forces, treat charge as a fundamental component of the mathematical structure of the universe. In this sense, understanding charge is not merely about explaining why atoms behave as they do. It is about uncovering one of the deepest organizing principles of reality itself. In summary, charge is a fundamental property of matter that defines how particles interact, how atoms are structured, and how the universe functions. It is intrinsic to electrons, protons, and quarks, and it is essential for chemistry, biology, technology, and the stability of the cosmos. Without charge, there would be no atoms, no molecules, no life, and no coherent universe. Charge is not a secondary feature or a convenient label. It is a defining characteristic of matter itself, embedded in the very framework of physical law. Through this lens, we see that the question of why atoms have charge is not merely about particles. It is about the fundamental architecture of reality, the invisible principle that organizes matter and energy at every scale. Charge is universal, quantized, conserved, and symmetrical. It underlies forces, energy interactions, and the structure of the atom. From the smallest subatomic particles to the vast reaches of electromagnetic waves, charge governs the dynamics of everything. It is the invisible code that writes the rules of the universe, the thread that connects electrons to protons, atoms to molecules, and matter to life itself. Understanding charge is understanding the blueprint of reality, a blueprint written not in stone, but in the language of interaction, symmetry, and fundamental law. If you want, I can also continue with the fourth keynote in the same level of detail and length, so the speech can progress seamlessly. Do you want me to do that next? To understand why atoms have charge, it is essential to examine the insights provided by quantum mechanics. Classical physics, with its smooth trajectories and continuous forces, could explain many macroscopic phenomena but faltered when describing the atom's stability. Electrons orbiting a nucleus should, according to classical electromagnetism, radiate energy continuously, spiral inward, and collapse into the nucleus. Yet atoms are stable. Electrons do not fall into nuclei. This paradox was one of the central puzzles that led to the birth of quantum theory, a revolutionary framework that reshaped our understanding of matter, energy, and, critically, charge. The emergence of quantum mechanics began at the start of the 20th century with Max Planck, who proposed that energy is not continuous but quantized. In his study of blackbody radiation, Planck found that energy could only be emitted or absorbed in discrete packets, which he called quanta. This quantization was essential to resolve discrepancies between theory and experiment. Planck's constant, a fundamental number in physics, set the scale of these energy packets. Although Planck did not immediately connect his work to the charge of electrons, his introduction of quantization laid the foundation for understanding why electrons exist in specific energy states around a nucleus rather than collapsing inward. Following Planck, Niels Bohr applied quantization directly to the structure of the atom. In Bohr's model of the hydrogen atom, electrons could only occupy certain discrete orbits, each corresponding to a specific energy level. Transitions between these levels would result in the absorption or emission of energy in the form of photons. Bohr's model successfully explained the spectral lines of hydrogen, a problem that classical physics could not resolve. Importantly, Bohr's model demonstrated that the charge of the electron and the electromagnetic attraction to the positively charged nucleus work together within quantized energy levels to produce stable atomic structures. Charge alone does not dictate the behavior of electrons. It is the combination of charge and quantum rules that maintains atomic stability. The Bohr model, however, was only a stepping stone. It introduced quantization, but it still treated electrons as particles in fixed orbits. The next step, developed by Erwin Schrödinger, described electrons as wave functions spread out in probabilistic clouds around the nucleus. The Schrödinger equation governs these wave functions, defining the regions, orbitals, where electrons are most likely to be found. These orbitals are shaped by the balance between the attractive force of the nucleus, due to its positive charge, and the wave-like behavior of the electron. In this framework, charge determines the potential energy landscape in which the electron exists. The electron's negative charge pulls it toward the positive nucleus, while quantum mechanics prevents the electron from collapsing entirely, producing stable distributions of charge around the nucleus. This quantum perspective transforms our understanding of charge from a simple property of particles to a defining factor in the energy and behavior of atomic systems. The electromagnetic interaction between charged particles shapes the wave, functions of electrons, determines energy levels, and dictates chemical behavior. The energy associated with these interactions is quantized, leading to discrete atomic spectra and the possibility of forming molecules with specific properties. Charge is not just a static label. It actively participates in the dynamics of matter at the smallest scales. Quantum mechanics also introduces the concept of spin, an intrinsic property of particles associated with charge and magnetic moment. Electrons have spin and their spin interacts with their charge to produce magnetic effects. This interaction underlies the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously within an atom. The exclusion principle, combined with the Coulomb interaction between charged electrons, explains the arrangement of electrons in shells and subshells, the structure of the periodic table, and the chemical properties of elements. Here again, the nature of charge is central. The electromagnetic repulsion between electrons, combined with quantum rules, dictates how atoms are structured and how they interact with one another. Another crucial quantum concept is the idea of quantized electromagnetic fields. Photons, the quanta of the electromagnetic field, mediate interactions between charged particles. When an electron changes energy levels, it emits or absorbs a photon. These interactions are governed by quantum electrodynamics (QED), one of the most precise and successful theories in physics. In QED, the charge of a particle determines the strength of its interaction with the electromagnetic field. The electron's negative charge sets the coupling constant, controlling the probability of emitting or absorbing photons. This precise relationship between charge and field interactions explains phenomena ranging from the scattering of light by electrons to the fine structure of atomic spectra. Quantum mechanics also explains why atoms generally remain neutral. In multi-electron atoms, electrons repel each other due to their negative charge, while all are attracted to the positively charged nucleus. The balance of these forces, combined with the quantized energy levels of the electrons, produces stable configurations where the total positive and negative charges are equal. The neutrality of atoms allows matter to aggregate into larger structures without runaway electrical forces tearing it apart. If electrons carried different charges, or if charge were continuous rather than quantized, atoms could not form stable structures, and matter, as we know, it would be impossible. Charge also underlies the formation of chemical bonds in the quantum picture. When atoms approach each other, the negatively charged electrons interact with both nuclei, creating attractive forces that can hold atoms together. Covalent bonds involve the sharing of electron density between atoms, while ionic bonds arise when electrons transfer from one atom to another, creating oppositely charged ions that attract each other. The strength, directionality, and stability of these bonds all depend on the properties of electric charge and its interplay with quantum mechanics. Molecular shapes, reaction pathways, and even the properties of materials are therefore a direct consequence of the charges of subatomic particles interacting under quantum rules. At a deeper level, quantum mechanics shows that charge conservation and symmetry are fundamental. The electric charge of a system is tied to a symmetry known as U1 gauge invariance. This abstract mathematical principle states that the laws of physics remain unchanged under certain transformations related to the phase of the quantum wave function. Charge conservation emerges naturally from this symmetry. In other words, the existence and stability of electric charge are not arbitrary. They are mandated by deep mathematical principles underlying the universe. Quantum mechanics does not merely describe charge. It explains why charge behaves consistently and predictably. Moreover, quantum mechanics links charge to the existence of antiparticles. Every particle with charge has a corresponding antiparticle with opposite charge. The electron has the positron, the proton has the antiproton. These antiparticles arise naturally from the solutions to relativistic quantum equations, such as the Dirac equation. When matter and antimatter meet, their charges cancel, and energy is released in a precise, quantized manner. This connection between charge, quantum mechanics, and fundamental symmetries underscores the deep role that charge plays in the fabric of reality. Quantum mechanics also illuminates why charges appear in discrete units. The electron represents the smallest free negative charge, and all other observable charges are multiples of this fundamental unit. This quantization is not merely a convenient description. It is a necessary outcome of the mathematical structure of quantum field theories. Fractional charges appear in quarks, but observable particles like protons and neutrons always have integer charges, reflecting the underlying rules of quantum chromodynamics. The discrete nature of charge ensures the stability of atoms and the predictability of chemical reactions. The influence of charge in quantum systems extends beyond the atom. It governs the behavior of condensed matter, including the properties of metals, semiconductors, and insulators. The movement of electrons in solids creates electrical currents, magnetism, and a host of electronic phenomena. Quantum mechanics explains phenomena such as superconductivity, the quantum Hall effect, and the behavior of electrons in nanoscale materials. In each case, the electron's charge is the central factor determining how it interacts with fields and other particles. Even the macroscopic universe is shaped by charge. While gravity dominates on cosmic scales, electromagnetic forces arising from charge govern the interactions of plasmas, ionized gases, and the behavior of charged particles in stars and interstellar space. The formation of stars, the structure of magnetic fields in galaxies, and the propagation of cosmic rays are all influenced by the interplay of charged particles at the quantum level. Charge is not merely a microscopic detail. It is a principle that resonates across scales, connecting the smallest components of matter to the largest structures in the cosmos. In summary, quantum mechanics revolutionizes our understanding of why atoms have charge. Classical physics can describe forces and trajectories, but it cannot explain the stability of atoms, the quantization of energy, or the discrete nature of charge. Quantum mechanics shows that charge is intrinsic to particles, determines their interactions, and is deeply tied to fundamental symmetries of nature. The electron's negative charge, the proton's positive charge, and the quantization of these charges are all natural consequences of quantum principles. Charge governs the structure of atoms, the formation of molecules, the behavior of materials, and even the organization of the universe. Through the lens of quantum mechanics, charge is not a secondary property, but a defining feature of reality. It shapes the potential energy landscape of atoms, dictates chemical behavior, enables technology, and underpins life itself. Quantum theory does more than describe charge. It explains its necessity, its discreteness, and its role in the structure of matter. Without charge, governed by quantum rules, atoms could not exist, molecules could not form, and the universe would be a fundamentally different place. Charge is, in essence, one of the deepest principles of the cosmos, and quantum mechanics allows us to see why it is both indispensable and exquisitely ordered. To understand why atoms have charge, it is necessary to examine the role of fundamental forces and the underlying interactions that govern particle behavior. While electrons and protons carry fixed charges, the way these charges interact is controlled by the electromagnetic force, one of the four fundamental forces of nature. This force is central not only to the stability of atoms, but also to the structure of molecules, the dynamics of materials, and even the processes that sustain life. By exploring the connection between charge and force, we gain insight into why charge exists and why it has the specific properties observed in nature. The electromagnetic force arises from the presence of charge. Oppositely charged particles attract, like charged particles repel. This simple rule leads to the rich complexity observed in atomic and molecular systems. Within an atom, negatively charged electrons are drawn toward the positively charged nucleus, but the quantum nature of electrons prevents them from collapsing into it. This balance between attraction and quantum mechanics produces stable atomic structures, which serve as the building blocks of matter. The precise magnitude of the electron and proton charges ensures that the attractive and repulsive forces are balanced in a way that allows atoms to exist. If charges were slightly different, atoms could either collapse or fail to bind, making chemistry and life impossible. The importance of charge is evident in chemical bonding. When atoms come close together, the negatively charged electrons interact with the positively charged nuclei of adjacent atoms. These interactions can lead to the formation of covalent bonds, where electrons are shared, or ionic bonds, where electrons are transferred, creating oppositely charged ions. In both cases, the forces between charges determine the strength, direction, and stability of the resulting bonds. This fundamental principle governs the entire architecture of molecules, from simple diatomic species to complex organic compounds and biological macromolecules. Without the precise properties of charge, the periodic table would lose its predictive power, chemical reactions would be unpredictable, and the molecules essential for life could not form. Charge also underlies the behavior of materials at the macroscopic level. In conductors, such as copper or aluminum, electrons are relatively free to move, allowing electric currents to flow. In insulators, such as glass or rubber, electrons are tightly bound to atoms, preventing significant movement. Semiconductors occupy a middle ground, where the flow of charge can be manipulated by doping with impurities or applying external fields. The ability to control charges in materials forms the foundation of modern electronics, enabling computers, smartphones, and countless devices. Without charge and its interactions, none of this technological infrastructure would be possible. The interplay between charge and force extends into magnetism. Moving charges generate magnetic fields, which in turn influence other moving charges. This relationship is described mathematically by Maxwell's equations, a set of elegant formulas that unify electricity and magnetism. The behavior of charges in motion gives rise to phenomena ranging from the operation of electric motors and generators to the dynamics of plasmas in stars. Charge is therefore not only responsible for static attraction and repulsion, but also for the rich variety of dynamic behaviors observed in nature. At the subatomic level, charge is tied to the structure of matter in even deeper ways. Protons and neutrons, though similar in mass, differ in their charge. The proton is positive, the neutron is neutral. Neutrons play a crucial role in stabilizing the nucleus by mediating the strong nuclear force, which overcomes the repulsion between protons. Yet the positive charges of protons determine the electromagnetic environment of the nucleus and influence the behavior of surrounding electrons. Electrons, by their negative charge, occupy specific quantum states and form orbitals. The overall distribution of charges within the atom creates an electromagnetic potential that governs the energies of these orbitals. Charge is therefore directly linked to the quantum mechanical stability of atoms. Another striking feature of charge is its quantization. Experiments such as Millikan's oil drop experiment have shown that electric charge exists in discrete units. The electron's charge is the fundamental unit of negative charge, and all observable charges are integer multiples of this unit. This quantization is critical for the predictability of chemical and physical processes. It ensures that atoms have well-defined structures, that electrons occupy discrete energy levels, and that chemical reactions proceed in consistent ways. Without quantization, matter would lack stability, and the very laws of chemistry would be altered. Charge is also intimately connected to the concept of conservation. In any closed system, the total electric charge remains constant. Electrons may move between atoms, ions may form and recombine, but the net charge does not change. This principle is not merely empirical. It arises from a deep symmetry of nature known as gauge invariance. Conservation of charge guarantees the stability of matter over time. Without it, the distribution of electrons and protons in atoms could fluctuate unpredictably, destroying the orderly structure of matter and preventing the formation of molecules. The role of charge extends beyond ordinary matter to exotic particles. Quarks, the constituents of protons and neutrons, carry fractional charges +2/3 or -1/3, which combine to form the integer charges of protons +1 and neutrons 0. These fractional charges are tightly constrained by the rules of quantum chromodynamics, the theory describing the strong nuclear force. The precise arrangement of quark charges ensures the overall charge of composite particles and, by extension, the behavior of atoms. This demonstrates that charge is a fundamental property that persists across multiple layers of matter, from subatomic particles to complex atoms. Charge also shapes the interaction of matter with light. Electrons absorb and emit photons depending on their energy states. These interactions are central to spectroscopy, allowing scientists to identify elements, understand chemical bonds, and probe the structure of matter. The coupling between charge and electromagnetic fields is fundamental to both natural processes and modern technology. Without the charges of electrons and protons, light could not interact with matter in the way it does, and the phenomena of reflection, refraction, absorption, and emission would not exist. In biological systems, charge is indispensable. Cells maintain electrical gradients across membranes, which are essential for processes such as nerve impulse transmission, muscle contraction, and the transport of ions and molecules. Proteins fold into specific shapes guided by the attraction and repulsion of charged amino acids. DNA double helix is stabilized by interactions involving charged phosphate groups. Even the basic metabolism of cells relies on the controlled movement of ions. The negative and positive charges of subatomic particles, therefore, underpin the molecular machinery of life itself. Charge also interacts with symmetry principles at the most fundamental level. Particles have corresponding antiparticles with opposite charge, a relationship predicted by relativistic quantum mechanics. For example, the electron has the positron, the proton has the antiproton. These symmetries are not arbitrary. They are dictated by the mathematical structure of quantum field theory. The existence of antiparticles and the preservation of charge during particle-antiparticle interactions illustrate that charge is a deeply embedded aspect of physical law, governing processes from particle collisions to the early evolution of the universe. Moreover, charge is central to the behavior of matter at extreme conditions. In plasmas, where electrons are stripped from atoms, the collective behavior of charged particles creates phenomena such as solar flares, auroras, and the interstellar medium. In superconductors, the pairing of electrons into Cooper pairs results in resistance, free currents. In semiconductors, the precise arrangement of charge carriers enables the operation of transistors, which form the backbone of modern electronics. Across these diverse systems, charge determines behavior, interactions, and emergent properties. Charge also determines how atoms respond to external fields. When an atom is placed in an electric field, the distribution of its electrons shifts relative to the nucleus, creating a dipole moment. This polarization affects interactions with neighboring atoms, influencing the material's dielectric properties. Magnetic fields interact with moving charges to produce currents and magnetic moments, which influence the behavior of electrons in solids and the alignment of spins in ferromagnetic materials. Charge, therefore, is not only fundamental to atomic structure, but also to the emergent properties of materials and the phenomena of condensed matter physics. Finally, charge is central to the broader structure of the universe. While gravity dominates large-scale structures like stars and galaxies, electromagnetic forces govern the behavior of charged particles, shaping plasmas, magnetic fields, and cosmic radiation. The balance of positive and negative charges in matter ensures neutrality on large scales, allowing galaxies, planets, and stars to form without being torn apart by electromagnetic forces. Charge is the invisible principle that connects the microscopic rules of atomic physics with the macroscopic architecture of the cosmos. In conclusion, the existence and properties of electric charge are deeply intertwined with the forces and interactions that define the universe. Charge is intrinsic to particles, governs atomic and molecular structure, enables chemical reactions, drives biological processes, and underlies modern technology. It is conserved, quantized, and governed by fundamental symmetries, linking the behavior of subatomic particles to the behavior of matter on cosmic scales. By understanding charge and its interactions, we uncover one of the most fundamental principles of reality. Charge is not a mere label or incidental feature of atoms. It is a defining characteristic that shapes the structure, dynamics, and complexity of everything in the universe. To understand why atoms have charge, it is crucial to explore the interplay between the intrinsic properties of subatomic particles and the fundamental forces that govern their interactions. By this point, we know that electrons carry negative charge, protons carry positive charge, and neutrons are neutral. But the mere existence of these charges is not sufficient to explain the complexity and stability of atoms. To truly grasp why charge exists and how it shapes matter, we must examine the underlying principles of particle physics, the forces at play within the atom, and the symmetries that regulate the behavior of matter on all scales. At the heart of the atom lies the nucleus, composed of protons and neutrons. The protons, each carrying a positive charge, create a strong electric field that attracts the negatively charged electrons surrounding the nucleus. This attraction is what binds the electrons to the atom and prevents them from drifting off into space. Neutrons, though neutral, are vital because they provide additional mass to the nucleus and help mediate the strong nuclear force that keeps protons from repelling each other violently. Without neutrons, the repulsive forces between protons would destabilize the nucleus, preventing the formation of stable atoms. Charge, therefore, is intimately connected to the structural integrity of matter. The electron itself is more than just a negatively charged particle. It is a quantum entity with wave-like properties. Schrödinger's equation describes electrons as occupying probabilistic regions around the nucleus, known as orbitals. The negative charge of the electron determines how it interacts with the positively charged nucleus, shaping the energy levels of these orbitals. This quantized structure is not arbitrary. It arises from the combination of the electron's charge, its quantum mechanical nature, and the electromagnetic force. Without these factors, electrons could not exist in discrete energy states, and atoms would be unstable. Charge is also the reason why matter can interact in such intricate ways. The electromagnetic force, mediated by charged particles, governs the formation of chemical bonds. Covalent bonds involve the sharing of electrons between atoms, while ionic bonds result from the transfer of electrons and the resulting attraction between oppositely charged ions. Hydrogen bonding and van der Waals forces, which are weaker interactions, also depend on the distribution of charge within molecules. These forces create the diverse chemical landscape that underlies all of chemistry and biology. Charge is the invisible glue that binds matter together, enabling the formation of complex molecules and, ultimately, life itself. At a deeper level, the behavior of charge is dictated by symmetries and conservation laws in nature. Electric charge is conserved. In any isolated system, the total charge remains constant. This principle is not merely empirical. It emerges from a fundamental symmetry known as gauge invariance in quantum field theory. Gauge invariance ensures that physical laws remain unchanged under specific transformations of the wave function, leading naturally to the conservation of charge. This connection between symmetry and conservation explains why charges are always precisely balanced in neutral atoms, and why the universe exhibits such regularity in the behavior of matter. The existence of fractional charges in quarks further illustrates the fundamental nature of charge. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. Up quarks carry +2/3 of the elementary charge, and down quarks carry -1/3. These fractional charges combine to produce the integer charges observed in protons and neutrons. The strong force, which binds quarks together inside nucleons, operates alongside the electromagnetic force. The balance of these forces ensures the stability of atomic nuclei. The specific arrangement and combination of quark charges are dictated by the fundamental symmetries of quantum chromodynamics, demonstrating that charge is embedded at the deepest levels of matter. Electrons, being negatively charged, interact not only with the nucleus, but also with each other. The repulsion between electrons, governed by their like charges, plays a key role in the arrangement of electrons in shells and subshells. The Pauli exclusion principle, which arises from the quantum property of spin, states that no two electrons can occupy the same quantum state simultaneously. This principle, combined with the repulsive effect of charge, explains why electrons fill orbitals in a specific order and why atoms have characteristic sizes and chemical behaviors. Charge is therefore not only essential for attraction to the nucleus, but also for the organization of electrons within the atom. Charge also determines the interaction of matter with light. Photons, the quanta of the electromagnetic field, interact with charged particles, particularly electrons. When an electron absorbs a photon, it moves to a higher energy level. When it emits a photon, it returns to a lower level. These interactions underpin the emission and absorption spectra of elements, which allow scientists to identify materials and study the composition of distant stars and galaxies. The behavior of light in relation to matter, including phenomena such as reflection, refraction, and fluorescence, is ultimately controlled by the charges of subatomic particles. Without charge, these interactions would not exist, and the observable universe would be profoundly different. The role of charge extends beyond individual atoms and molecules to macroscopic materials. Conductors, insulators, and semiconductors all owe their properties to the behavior of electrons under electromagnetic forces. In metals, free electrons can move easily, creating electric currents and enabling conductivity. In insulators, electrons are tightly bound, preventing current flow. Semiconductors allow controlled manipulation of charge carriers, forming the basis of modern electronics. Magnetism, too, arises from the movement and alignment of charges, particularly the intrinsic spins of electrons. Charge is therefore central to the electrical and magnetic properties of materials, shaping both natural phenomena and human technology. In biological systems, charge is indispensable. Cells maintain voltage gradients across membranes through the controlled movement of ions, which are charged atoms or molecules. These gradients drive processes such as nerve impulse transmission, muscle contraction, and the active transport of substances. Proteins fold into specific three-dimensional structures guided by the attraction and repulsion of charged amino acids. DNA, with its negatively charged phosphate backbone, forms the iconic double helix stabilized by interactions with other molecules. Charge is not a peripheral feature. It is central to the organization and function of life at the molecular and cellular levels. Charge is also central to the stability of matter on larger scales. While gravity dominates the structure of planets, stars, and galaxies, the electromagnetic force determines how plasma behaves, how magnetic fields are structured, and how cosmic rays propagate through space. The balance of positive and negative charges in atoms ensures neutrality on macroscopic scales, allowing stars, planets, and interstellar clouds to exist without being torn apart by electric forces. Charge links the microscopic world of particles to the macroscopic universe, demonstrating its fundamental role in shaping reality. The quantization of charge adds further significance. Millikan's oil drop experiment confirmed that charge exists in discrete units. The electron's charge is the smallest free unit of negative charge, and all observable macroscopic charges are multiples of this fundamental unit. This quantization is essential for the stability of atoms, the consistency of chemical reactions, and the predictability of physical laws. Fractional charges in quarks combine to produce integer charges in composite particles, demonstrating that quantization is a fundamental feature of matter, not merely a convenient approximation. Charge is also closely tied to symmetry in the universe. For every charged particle, there exists an antiparticle with opposite charge. The electron has the positron, the proton has the antiproton. These relationships are predicted by relativistic quantum mechanics and confirmed experimentally. When particles meet their antiparticles, they annihilate, releasing energy. This symmetry reflects the deep connection between charge, energy, and the fundamental laws governing matter. Charge is therefore not only a property of individual particles, but a guiding principle of universal order. Finally, charge is intimately connected to energy and forces in the atom. The electromagnetic attraction between electrons and the nucleus determines the potential energy landscape in which electrons exist. The repulsion between electrons shapes the arrangement of orbitals. The interplay of these forces gives rise to discrete energy levels, chemical reactivity, and the formation of molecules. Without charge, these structures would collapse. Atoms would not form stable configurations, and matter as we know it could not exist. Charge is the organizing principle that allows complexity to emerge from simplicity. In conclusion, the existence and behavior of electric charge explain the structure, stability, and diversity of matter. Charge is intrinsic to subatomic particles, governs their interactions, enables chemical bonding, drives biological processes, and underpins technological advances. It is quantized, conserved, and deeply connected to the symmetries of nature. From the stability of atomic nuclei to the behavior of electrons in orbitals, from the interactions of light with matter to the formation of stars and galaxies, charge shapes the universe at every scale. Charge is not an incidental feature of atoms. It is a fundamental principle that defines the architecture of reality, ensuring the stability, complexity, and coherence of the material world. To understand why atoms have charge, it is important to consider the broader implications of charge on the stability, interactions, and evolution of matter. While we have explored the structure of atoms, the behavior of subatomic particles, and the role of fundamental forces, the final piece of the puzzle lies in recognizing how charge governs the complexity and diversity of matter on all scales. Charge is not only intrinsic to electrons and protons. It is a principle that shapes chemical reactions, biological processes, materials science, and even the cosmic order of the universe. At the atomic scale, charge is the force that holds electrons in their orbits around the nucleus. The negative charge of the electron is attracted to the positive charge of the protons in the nucleus, creating a stable system. Quantum mechanics ensures that electrons occupy discrete energy levels, but it is the interplay of charge and quantum rules that prevents collapse. This delicate balance allows atoms to exist as coherent, stable entities rather than chaotic clouds of particles. The fact that electrons and protons have equal but opposite charges ensures electrical neutrality in most atoms, allowing them to combine into molecules without being torn apart by excessive forces. Chemical bonds, which are fundamental to matter, arise directly from the interactions of charges. Covalent bonds form when electrons are shared between atoms, creating stable electron clouds that bridge two nuclei. Ionic bonds arise when electrons transfer from one atom to another, producing oppositely charged ions that attract each other. Even weaker interactions, such as hydrogen bonding and van der Waals forces, depend on the subtle distribution of charges within molecules. These interactions give rise to the vast array of chemical compounds that make up our world. Without the specific properties of charge, chemistry would lose its predictability, molecules could not form reliably, and the complex structures required for life would be impossible. Charge is also central to the behavior of materials. Metals conduct electricity because their electrons are free to move under the influence of electric fields. Insulators resist electrical flow because their electrons are tightly bound. Semiconductors allow precise control of charge movement, forming the foundation of modern electronics. Magnetic properties, too, arise from the spin and movement of electrons, which are intrinsically charged. The ability to manipulate charge has revolutionized technology, enabling the creation of computers, smartphones, and electrical grids. Without the intrinsic charge of electrons and protons, these innovations would not exist. In biological systems, charge is indispensable. Ion gradients across cell membranes drive processes such as nerve impulse transmission, muscle contraction, and energy production. Proteins fold into functional shapes because of electrostatic interactions between charged amino acids. DNA negatively charged phosphate backbone allows it to interact with proteins and form the double helix. The precise distribution and balance of charges at the molecular level underlie the very processes of life, illustrating that charge is not merely a physical property, but a foundation for biological complexity. Charge also governs the interaction between matter and light. Electrons absorb and emit photons according to their energy states, a principle that explains atomic spectra and enables technologies such as lasers, LEDs, and solar cells. The coupling of charge with electromagnetic fields is central to understanding light, matter interactions, and demonstrates the universal influence of charge beyond static attraction and repulsion. At the subatomic level, the combination of charges in quarks produces the familiar charges of protons and neutrons. Fractional charges combine according to the rules of quantum chromodynamics, ensuring the stability of nuclei. This intricate arrangement underscores that charge is a fundamental, non-arbitrary property of matter. Even at the smallest scales, charge is essential for maintaining the architecture of atoms and, by extension, all matter. Charge is also conserved and quantized. The electron represents the smallest unit of negative charge, and all observable charges are multiples of this fundamental unit. Conservation of charge ensures that in any closed system, the total charge remains constant, a principle essential for the stability of atoms and the predictability of chemical reactions. Quantization and conservation together create a coherent, orderly universe in which atoms and molecules behave consistently over time. On a cosmic scale, charge influences the behavior of plasmas, magnetic fields, and interstellar matter. While gravity dominates large-scale structures like galaxies and clusters, electromagnetic forces arising from the distribution of charges control the dynamics of charged particles, the formation of stars, and the propagation of cosmic radiation. The balance of positive and negative charges in matter ensures that macroscopic structures remain stable and do not disintegrate under electrical forces. Symmetry plays a fundamental role in the behavior of charge. Each particle with charge has a corresponding antiparticle with opposite charge. These relationships, predicted by relativistic quantum mechanics, reflect deeper principles governing the laws of nature. When matter and antimatter meet, their charges cancel, releasing energy. This symmetry ensures balance at the most fundamental level, demonstrating that charge is embedded in the very structure of physical law, governing processes from particle interactions to evolution of the universe. Ultimately, Charge is the organizing principle that allows complexity to emerge from simplicity. From the stability of atoms to the formation of molecules, from the flow of ions in cells to the propagation of light and electromagnetic waves, charge shapes the behavior of matter and energy across scales. It is intrinsic, quantized, conserved, and symmetrical, providing the foundation for both the microscopic world of particles and the macroscopic universe we observe. In conclusion, the presence of charge in atoms is not a trivial feature, but a fundamental necessity. It dictates how electrons interact with nuclei, how atoms form stable configurations, how molecules bond, and how materials conduct electricity or exhibit magnetism. Charge underpins life itself, governs chemical reactions, and enables the technologies that define modern civilization. Beyond the microscopic world, it influences cosmic phenomena and reflects deep symmetries in the laws of physics. Charge is the invisible thread connecting the smallest particles to the vast universe, providing stability, coherence, and complexity. Understanding why atoms have charge is to understand one of the most profound organizing principles of nature, revealing the hidden architecture that shapes reality at every level.